Okay, so, well, I would like to thank the organizers for providing me the opportunity to be here at this most impressive meeting with these many, wonderful presentations that report such amazing progress in quantum technologies. So, I would like to now take a slightly different tack. So we want to go a bit more on the potential use of quantum technologies, quantum control for the life sciences. And I will report on work from the community, but also from work that we are doing in this newly established Center for Quantum Biosciences, where we bring together theoretical physics, experimental physics, chemistry, and real medics to work together to try and explore this interface. And so most of the talks that we have been listening to so far have been concerned with quantum computing, quantum simulations, and it's clear that really a full-scale quantum computer will in the end need millions of qubits to be controlled to an extraordinary degree. And so this is surely an extraordinary challenge. So I would like to set my sights much lower than that. And I would like to explore what we can do with the control of a few spins, a handful, but maybe in a less clean environment, namely sort of more geared towards the life sciences. And so that will be the goal of the talk, and there will be two main topics that I will be exploring here. And so the first one starts with the color center in diamond. That's a particularly interesting type of quantum sensor, and it's based on lattice defects in diamond. So up there you see a nice diamond with a color, and origin of the color can originate from different effects, but an important one are actually lattice defects. And we are interested in the NV center, which is a substitutional nitrogen that has a neighboring vacancy. And the dangling electronic bonds that you have when it's negatively charged, they together can form a spin singlet in the ground state. And because this defect center actually provides color to diamond, that means that we can actually also control and read it out by laser light. And so we have a spin degree of freedom that we can manipulate by microwaves and read out by a laser light. And of course, like in atoms, here we have the Zeeman effect. So therefore, this spin triplet state will be sensitive to magnetic fields and therefore can be used as a sensor for even potentially single nuclear spins. And so this work, this system, of course, it was around for a while, and even in the 80s, people were looking at ensembles of these systems and did optically detected magnetic resonance. But then in the pioneering work, Jörg Wrachtrup managed to do these experiments on single NV centers, and that really made a very big difference in the development of this type of technology. And so what we are doing here, therefore, is we use these external control fields, the microwaves and the lasers, to connect via the microwaves the nuclear spins with the electron spins, and via the laser the electron spin with a photon. And therefore we provide a transport path that can either transport information about the nuclear spin to the photon field where we can see it, or in the same vein, transfer entropy from the nuclear spins and thereby cooling them. And so these are the two aspects that I will be exploring in this talk and its applications. So first thing that you can do with this system is you can just look actually at the coherence time of the NV center and how it is actually influenced by its environment. And that gives you actually the opportunity to, for example, start to measure the presence or absence of radicals in cells. And even now with temporal resolution, where you can see certain redox or reactions starting to take place with second timescale resolution. And that can give you new insights into cell processes or processes of life in cells. But I would like to go further, and this is because this was really looking for fluctuations. But what you would like to also do is you want to really see coherent signals from the environment. And here you have to do some control. And what you see here is you have the NV center in the middle, and this is an electron spin. And it has a resonance frequency that is gigahertz. And you want to see, let's say, megahertz frequencies of megahertz frequency magnetic fields that are emanating from the nuclear spin. So you have to bridge this energy gap somehow. And that's what you do by microwave control. So what you're doing is you have this time-dependent signal coming in, and sometimes it's positive, sometimes it's negative because it's oscillating. So what you have to do is you have to control the sensor in such a way that you flip this spin in phase with the incoming signal. So whenever the signal is negative, to change a sign, you change the sign of the sensor, and therefore you accumulate coherence in a positive manner over a long period of time. And when you do this, you actually use the frequency of the time separation between the pulses in a suitable way, and that creates for your frequency filter. So depending on the pulse spacing, you're sensitive to particular frequencies. And the length of the filter or the length of the pulse sequence gives you an information about the spectral resolution, which is the inverse of the length of that pulse sequence. So that you can use indeed, and over the years, people have worked on this and detected electron spins and eventually nuclear spins inside of diamond, and eventually, actually, even nuclear spins outside of diamond using an NV center in the diamond. So above the surface of diamond, you can now see nuclear spins sitting there with single nuclear spin sensitivity. And you can identify that these are the right sort of spins by tuning the magnetic field and also localize them in space. You can even drive this further now, and we've made first steps towards actually now taking nanoscale diamonds, placing them into the cell, and starting to use this microwave control to stabilize the electron spin to make it really suitable as a sensor for magnetic signals inside of the cell. There's still some way to go here because this can also lead to temperature increases and one has to optimize these control sequences, but there are interesting steps that you really can place a quantum sensor inside of a living cell. Now, when you look at this, above, you see also the resonance lines, and you see that they are actually quite broad. I mean, the scale is megahertz, and so these are kilohertz with widths of these resonances. And this is not what you are used to from nuclear magnetic resonance. There you go to a nuclear magnetic resonance machine, you get hertz resolution. And so the question is, what can we do about this here? So here I explained that this is limited, when you do it naively, by the length of the pulse sequence that you are using, because that gives you the width of the spectral filter. But it turns out that you can do better. So if you do the measurements independently, you apply the pulse sequence, you can take a data point, then you wait a while, you apply it again, you do this in a phase incoherent way, then you really have this resolution limit that is given by the length of the pulse sequence. But you can do better by actually, well, probably, okay, by actually do this measurement in a coherent sequence. So you take additionally a clock, you take the first measurement, you take a data point, but now you keep track of the phase, and the next measurement will be taken in phase. And so therefore you can now start to sample this time-dependent signal in a phase-coherent manner, and now the resolution limit is not the length of the individual pulse sequence, but actually the length of the entire signal that you are picking up. And that works because you are now using an external clock that allows you to keep track of the phase. And so this is also indeed much closer to what, let's say, standard NMR would be doing. And this allows us now to take the resolution limit from this kilohertz to actually, again, the hertz regime. And so now what is also nice about this setting, when you analyze it, you see that actually the frequency resolution scales like 1 over t to the 3 over 2, so 1 to the t over 1.5, which seems to be much faster than the Heisenberg limit. So that should make you worried, because if I can determine frequency, I can actually indirectly determine magnetic field, because magnetic field determines Larmor frequency of the nuclei. And so it seems as if I could, with this scheme, could actually beat the Heisenberg limit of spectral resolution. This is not true, because in this assumption here, in this expression, I have assumed that there's no back action of the NV center or the detector onto the nuclei. So this will hold true for as long as you can treat the signal as being classical. But as soon as, at some point, there will be a back action of the NV center onto the nuclei, There's no other dephasing, of course. And then you will go back to the standard Heisenberg limit or even the shot noise. So there's no contradiction. So this is nice. So now we can have this setting where we have NV centers underneath the surface. We use them to try and detect nuclear spins above the surface. And now we have the chance to do this actually with a Hertz resolution like standard and NMR could do. So this, in a way, solves the resolution limit, but it still is very challenging to really see a measurable signal, especially when you want to go from very highly concentrated solutions to something that is much more like, let's say, a single cell and looking for metabolites in that cell, because this has millions of times lower concentrations than, let's say, 100% solution of the target. So you have to do something to increase the signal. And so there are various ways of what one can do. So one way is that we have to now take the target and we actually have to polarize the nuclear spins of the target so as to give a much stronger signal response. So they should not be in thermal equilibrium, but actually really 10 or 50 or 100% polarized, which could increase your signal by a 10,000-fold, potentially, or even 100,000-fold. And so therefore you can decrease the minimal detectable concentration. And so, I mean, we worked this out in theory, but there's a wonderful demonstration of that by the Harvard group that actually used this to enhance the signal from the NV centers, from the nuclear spins. But still, this is still not quite enough to see, let's say, the metabolism or very rare metabolites. You also have to take into account that what you get here is a very noisy signal, and you have to really try and use the best methods to extract the information from this signal. A little bit like gravitational wave detectors use a lot of signal processing methods to uncover the signal from the underlying noise, including they are putting in a lot of prior knowledge to what they want to see. And here, we should do the same, really. Instead of just taking a time series and taking a Fourier transform and trying to detect a completely unknown frequency, we should make use of the fact that we are looking for a hydrogen signal, for example. We know roughly what we are looking for. We know what the detection characteristics of the NV centers are. We know many characteristics of the device. So we should take all of this into the data analysis. And when you're doing this, you can extract from the same data actually a signal much more efficiently, and you can reduce the minimal detectable concentration by another factor of 10 or 100 or so by taking into account all the knowledge that you have about your apparatus. And then you would like to go even further, and you would like, for example, to use quantum logic enhanced sensing, where you use let's say, nearby nuclear spins in the NV center to accumulate signals more efficiently. And there's a very nice work from the Harvard group that has actually implemented this, and they gained significant improvement in the signal to noise ratio. And when we put all these things together, then we may have a chance to actually really do NMR measurements on a single cell on the surface of a piece of diamond, and not only of the cell, but actually to see its metabolism. And that would be very interesting, for example, in cancer research, where we know that there's a bigger heterogeneity of the cells. And so it would be very interesting to look at them individually rather than just looking at the average of those cells. So that is ongoing work that is taking place in Harvard, in Munich, in Ulm, that's driving towards this goal to really push NMR to a new limit using also these control methods. Now, we're talking about cancer. One thing is to observe it. Another thing is actually maybe to treat it. And here I would like to look at what doctors are doing nowadays. So when a patient has a tumor, typically you make certain tests, and then a doctor takes from a large group of available treatments, picks one, and then applies it to the patient. And then we apply this for a while, and we look whether the tumor is shrinking or not. And that is typically taking a long time. This can take up to a month or so, or even many months. And this is a long time that we have to wait before we can decide whether the treatment is working or not. And of course, before the tumor is shrinking, the cells in the tumor must start to die. That happens earlier until it's a detectable amount. But even that is still a long time. But before the cells are dying, actually their metabolism changes. And so what we really would love to do is we would love to see in a patient whether the tumor's metabolism responds to the treatment. And if it does, we can see this within days. And that would allow us then to decide very quickly whether the treatment is working or not, and therefore can adjust it more rapidly. And again, the problem is that one technology that might be able to do this is PET-CT. The problem is that it's radioactive, and it's also often gives false positives, and it's not a technology that you can use every day. So what we would like to do is we would like to use magnetic resonance imaging that you can apply every day. It's not harmful in any way, and detect the metabolism of a tumor. And the problem with that is, why don't we do this already? Well, the problem is that the concentrations of the metabolites is extremely small, and we will not see them. It's just the signal is too small. And so therefore, again, we have to somehow enhance the signal of metabolites to enhance the signal to make it visible in the MRI. And of course, we cannot do this in the body. We have to do this externally. And so what we need to do is we need to take metabolites, we mark them with carbon-13 atoms, and then those carbon-13 atoms we want to hyperpolarize. So to increase the signal from those atoms, and by using carbon-13, we have much less background because this line is very much shifted from the hydrogen in the body, and there's very few carbon-13. And so this gives us a relatively background-free measurement. So how could you go about this? Well, what you need for this is you need a readily available source of low entropy, so a coolant, basically. And then you need to bring it in close contact with your target molecules. And then you need to take it you need to control the dynamics in such a way that you can transfer the entropy from the coolant onto the target nuclei. And this procedure has to be really versatile, so you don't want to have to invent something new for every molecule that there might be. And there is a technology that can do that. It's even you can buy it. It's very expensive, but you can buy it. And it uses electron spins at very low temperatures at very high magnetic fields, so that they actually just thermalize to a highly polarized state themselves. And then you use microwaves to transfer this polarization to nuclear spins. And you can imagine this is a very slow process because the thermalization, you have to do it repeatedly, of the electron spin is very slow. And so this is possible as in principle, but it takes hours to make one sample, and it's very fragile technology. So you could try and accelerate this by using NV centers, and that's certainly what we tried, by using light to first polarize the electron spin now within microseconds, so much faster at room temperature without a strong magnetic field, and then transfer the polarization. And while this works, it does not really work well enough to turn this into a commercial device. And because partly it falls down on this bringing things into close contact. The NV centers are 3 nanometers from the target, and that is very far from making an efficient transfer of polarization. And so therefore, we had to look for something else, and that is indeed para-hydrogen induced polarization. This was invented by Bowers and Weiterkamp in the 80s. But it didn't really gain much traction for a long time. And this had various reasons. So first, its versatility. And so in 2015, there was a new idea of how to improve this, how to make easily a connection between para-hydrogen, which is in a singlet state, and therefore extremely pure. And this has to be connected to molecules in a pairwise addition of this hydrogen molecule. And this requires some chemistry that was introduced by Rainieri and Aimé in 2015. So this works well now, but now we still need the control to really control the dynamics of a small spin systems, a few hydrogen atoms, a few deuterium atoms in the molecules, and the target carbon-13. So this is a handful of spins, and you have to now make a very efficient dynamics for the transfer of the hydrogen singlet order to the carbon-13 atoms. And now here, the community has started to develop these things, but the sequences were not quite so efficient. And it turns out that you can actually make analogy, mathematical equivalence actually, between the multispin system in the para-hydrogen-induced polarization and the situation that we have in standard DMP with NV center, electron spins, and nuclear spins. So we can translate all these sequences that we have developed in the NV arena to this para-hydrogen-induced polarization arena. And normally, we in NV centers, we learned from the NMR community. But it turns out that now, from the things that we invented in the NV regime, we can actually make a contribution to the para-hydrogen-induced polarization community. In the NV center arena, we introduced some pulse sequences, analytically constructed, that were very, very robust. And they actually turned the state of the art on the left-hand side in terms of robustness of polarization sequences into quite another thing now with this new sequences. So red is good, and the larger the area, the better, of course, the more robust you have. And so in this way, we can introduce now much more ideas from NV center physics to this field and make much more robust polarization sequences that turn this from something that you can make workable in a lab full of postdocs and PhD students into actually a device that you can really, let's say, a theoretical physicist can even operate, because it needs a press of a button, and out comes, after 90 seconds or so, comes the polarized liquid. And here you can see really on the left-hand side now the first pictures, MRI imaging of metabolites that have been inserted into the body. And if you want to buy it, now this is a device that you can really buy to provide you now, using some simple quantum control methods of small spin systems, a device that can enhance your MRI imaging and hopefully will inform doctors about how to treat cancer better. And with that, I would like to close. So this is a different type of quantum application, much simpler than many of the things we have seen here, but in a much more dirty environment in that sense, which makes it, again, challenging. But it is possible to turn this now actually from, fundamental research into commercial applications. And so this is work that a lot of people contributed, the PhD students there in bold. And also I would like to acknowledge the very, very fruitful collaboration with the experimental group of Fyodor Zheletsko, with whom we developed many of these things, and also with my former PhD student, Eli Schwartz, who is now CTO of Envision, that drives this from the lab to the real world now. Thank you.